So, chapter three is essentially a review chapter with one little add on. And that one little add on that could be new to you, but maybe not, is the complex number system. So, up until this point, we only dealt with the real number system. So, that is your natural, your whole, your integers, your rational, and your irrational numbers. But when we're going to be solving quadratic equations, some quadratic equations do not have any real number solutions. So for example, if I ask you to solve where does x squared equal -1, well, if you think about solving, and this will be part of the lesson, but again, it should be review, is that if you were to get rid of a square, the opposite of squaring is taking a square root. So if I was to solve that, I would get x equals plus or minus the square root of -1. And what we're just going to talk about in this lesson is what to do with a -1 or a square root of -1. So it's not technically a real number, although there's lots of debate on this. So up until now, anytime we've gotten a square root of a negative, we've just said no solutions and we've moved on. But now we're going to learn that the square root of -1 is actually a number that we need to deal with, and it does exist in a way. So I'm going to start off just by showing you this little video. It's part one of like a 6-part series, but I kind of just like some of the things they say and just to kind of inspire you how complicated math can get a little bit. So just one second.
Let's say we're given the function f of x is equal to x squared plus 1. We can graph our function and get a nice parabola. Now, let's say we want to figure out where the equation equals 0. We want to find the roots. On our plot, this should be where the function crosses the x-axis. As we can see, our parabola actually never crosses the x-axis, so according to our plot, there are no solutions to the equation x squared plus 1 is equal to 0. But there's a small problem. A little over 200 years ago, a smart guy named Gauss proved that every polynomial equation of degree n has exactly n roots. Our polynomial has a highest power or degree of 2, so we should have 2 roots. And Gauss's discovery is not just some random rule. Today we call it the fundamental theorem of algebra. So our plot seems to disagree with something so important, it's called the fundamental theorem of algebra, which might be a problem. What Gauss is telling us here is that there are 2 perfectly good values of x that we could plug into our function and get 0 out. Where could these 2 missing roots be? The short answer here is that we don't have enough numbers. We typically think of numbers existing on a one-dimensional continuum, the number line. All our friends are here. 0, 1, negative numbers, fractions, and even irrational numbers like root 2 show up. But this system is incomplete. And our missing numbers are not just further left or right, they live in a whole new dimension. Algebraically, this new dimension has everything to do with a problem that was considered impossible for over 2,000 years, the square root of -1. When we include this missing dimension in our analysis, our parabola gets way more interesting. Now that our input numbers are in their full 2-dimensional form, we can see how our function x squared plus 1 really behaves. Our function does cross the x-axis. We were just looking in the wrong dimension. So why is this extra dimension that numbers possess not common knowledge? Part of the reason is that it has been given a terrible, terrible name. A name that suggests that these numbers aren't even real. In fact, Gauss himself had something to say about this naming convention. So yes, our missing dimension is comprised of numbers that have been given the ridiculous name imaginary. Gauss proposed these numbers should instead be given the name lateral, so from here on, let's let lateral mean imaginary. To get a better handle on imaginary, I mean lateral numbers, and really understand what's going on here, let's spend a little more time thinking about numbers themselves. Early humans really only had use for the natural numbers, that is 1, 2, 3, and so on. This makes sense because of how numbers were used. So to early humans, the number line would have just been a series of dots. As civilizations advanced, people needed answers to more sophisticated math questions, like when to plant seeds, how to divide land, and how to keep track of financial transactions. The natural numbers just weren't cutting it anymore, so the Egyptians innovated and developed a new high-tech solution: fractions. Fractions filled the gaps in our number line and were basically cutting edge technology for a couple thousand years. The next big innovations to hit the number line were the numbers 0 and negative numbers, but it took some time to get everyone on board. Since it's not obvious what these numbers mean or how they fit into the real world, 0 and negative numbers were met with skepticism and largely avoided or ignored. Some cultures were more suspicious than others, depending largely on how people viewed the connection between mathematics and reality. And this is not all ancient history. Just a few centuries ago, mathematicians would intentionally move terms around to avoid having negatives show up in their equations. Suspicion of 0 and negative numbers did eventually fade, partially because negatives are useful for expressing concepts like debt, but mostly just because negatives kept sneaking into mathematics. It turns out there's a whole lot of math you just can't do if you don't allow negative numbers to play. Without negatives, simple algebra problems like x plus 3 equals 2 have no answer. Before negatives were accepted, this problem would have had no solution, just like we thought our original problem had no solution. The thing is, it's not crazy or weird to think these problems have no solutions. In words, this algebra problem basically says, if I have 2 things and I take away 3, how many things do I have left? It's not surprising that most people who have lived on our planet would be suspicious of questions like this. These problems don't make much sense. Even the brilliant mathematicians of the 18th century, such as Euler, didn't really know what to do with negatives. He at one point wrote that negatives were greater than infinity. So it's fair to say that negative and imaginary numbers raise lots of very good, very valid questions. Like, why do we require students to understand and work with numbers that eluded the greatest mathematical minds for thousands of years? Why did we even come to accept negative and imaginary numbers in the first place when they don't really seem to be connected to anything in the real world? And how do these extra numbers help us explain the missing solutions to our problem? Next time, we'll begin to address these questions by going way back to the discovery of imaginary numbers.
All right, so whether you found that interesting or not, I thought it was kind of cool. Moving into that imaginary or lateral plane was just like, what? Okay, so these 2 imaginary x-intercepts actually do exist. Anyway, so what we are going to do is just deal with the number I. Or deal with the number square root of -1, really. And so mathematically, there is a purpose for this. There are solutions to the square root of -1. And so what we're going to do is learn how to do the algebra with this square root of -1. And the first rule that you need to learn is that they have called the square root of -1 I. It's called the imaginary unit, even though it's not really an imaginary number. And so what we're going to practice is writing these imaginary numbers in terms of I. So anytime you have a square root of a negative number, we are going to rewrite it in terms of I. In other words, you're going to take the square root of negative p and factor it into the square root of -1 and the square root of p, which is going to give you I root p, or root p I. So it's kind of up to you, the commutative property of multiplication. It doesn't matter whether it's 2 times 3 or 3 times 2. If you do I times root p or root p times I tend to use root p times I, even though that's not what the textbook had, just because when we learn how to write complex numbers, we usually write them as a plus bi, and that imaginary part's on the end. Plus, then it kind of feels like a variable. So first off, if I was to simplify the square root of -17, I would think of it as the square root of 17 times the square root of -1. And then you're literally just replacing the square root of -1 with an I. Now, oftentimes to show that this is a closed radical, you can put a little bip on the end, and that shows that it's just the square root of 17 times I. If you have something that's a perfect square, you're going to do the same thing. You've got the square root of 4, square root of -1, but then this time the square root of 4 is 2, and then the square root of -1 is I, so we get 2I. If you have something like the square root of -48, you're going to simplify that even further. So you're going to use your rules for simplifying radicals, which was part of the essential skills review, and you're going to look at 48. What are the 2 numbers that multiply to give you 48, where one of them is a perfect square? Any idea? Hopefully you're all thinking square root of 16 times the square root of 3 times the square root of -1. So then I can simplify this to 4 times the square root of 3 times I. Awesome. So now what I want you to do is I want you to practice. Now these three are essentially the same. I have thrown this negative out front just because I want you to realize that if you have negative square root of a negative, that negative just stays out front. And then it'd be times the square root of 13 times the square root of negative 1, but your answer would be negative square root of 13I. Okay, so then try these next two. So for this one, we're going to get negative square root of 64, square root of negative 1, which is going to give us negative 8I. And then lastly, with this one, we've got that negative out front. We've got a perfect square that goes into 12 of 4. 4 times 3 is 12. And then we've got that square root of negative 1, which is going to simplify to negative square root of 4 is 2, square root of 3I. Awesome. And again, if you wanted to write this differently, it could be negative 2I square root of 3, and it really doesn't matter where you put that I. Awesome. Go and practice those.